Hello. Today we'll be talking about spherical geometry. So let me just share my screen. Okay, I hope you can see my screen. So yes, today we'll be talking about spherical geometry. Before we start talking about what spherical geometry is, let's first talk about what we mean by a geometry. So by when we say a geometry, I mean all of you guys are probably familiar with the term Euclidean geometry, which is basically the same sort of geometry you've been studying in school throughout your 8th standard onwards, I guess. But yeah, so by Euclidean geometry, what we usually refer to is we mean by you consider the set of points which is given by R2, that is the points x comma y, where such that x and y are in are real numbers. So this is your set of points. Your set of points is a plane, and between any 2 points, you have a well-defined notion of a line. So you have lines, and these are what we call the straight lines. Lines in R2. We know what this means, and then we have a notion of what distance between 2 points is, what the angle between multiple 3 points is, and so on. So when we say that we want to define a geometry, we want to first primarily say what the points are in this space you're working with, and what we mean by lines in that space. And we would ideally also want to define a notion of distance between 2 points, so that lines correspond to, uh, like, if you have a line joining 2 points, then you would want to have that the length of the line segment contained between those 2 points is equivalent to the distance between those 2 points. Moreover, you would want some properties such that, like, between any 2 points, there exists a unique line. Let me not use this symbol in case some people are unfamiliar with the notation. So yeah, there is a unique line. And so how do you define Euclidean geometry? And so the way we Euclid define Euclidean geometry is by stating certain axioms. So like firstly, he said that, like, okay, the points we are working with is points in R2, and our lines are straight lines. And then there are some properties, and there are some properties like, um, any two right angles are equal in measure. And so there's a list of 5 axioms, 5 basic axioms, which were, you using these 5 very simple statements, which were decidedly unproven. We can derive the most complicated theorems in Euclidean geometry, because these are the defining axioms for Euclidean geometry. Among the 5 axioms was this one statement known as the fifth axiom, or known as this is also known as the parallel postulate. Postulate. This states that, for any line, and any point not on the line, there exists a unique, sorry, there is a unique line through the point parallel to the given line, to the given line. Yes. So if you have some line and you can choose any point not on this line, then what you cannot have is two lines passing through this point which are both parallel to your given line. You can have at most one line through this point parallel to the given line. Okay, so there was this statement seemed weirder than any of the previous statements. The previous statements all seemed like basic properties of a geometry that you would want to have for any geometry. It seemed very natural. This seemed sort of artificial, and for a large time, a lot of mathematicians tried to prove that this statement is not in fact an axiom, and like maybe you can prove this parallel postulate using the rest of the axioms. However, in a long time later, it was proven that this postulate is in fact a postulate. And the way you prove this is you define, so to prove that this is a postulate, you basically define a new geometry. By define a new geometry, I mean define like you specify your set of points, you specify your lines, and so on, so that which satisfies rest of Euclid's axioms, but not axiom 5, the parallel postulate. Once you do this, then it would mean that like using just the rest of the postulates, you cannot prove parallel postulate, because there are at least two different geometries which satisfy both the like all the other axioms, but like one satisfies the parallel postulate, one does not. So which means that like you really do need the parallel postulate to define Euclidean geometry. Uh, so one such way, like a priori, there are two ways in which parallel postulate was people were able to construct two different geometries for the plane. One is known as the hyperbolic geometry. Which in which the version of parallel postulate goes by given point and line not through the point. There exist infinitely many lines parallel through the point parallel to the given line. To line through point. So hyperbolic geometry is one way like this was constructed, and the second geometry that was constructed, this was by Lobachevsky. It was known as the elliptic or spherical geometry. And for this geometry, you would have that given a point and a line, there are, so these are two different things, there are no lines through the point parallel to the given line. Through point parallel to given line. So let's see how we can construct such geometry. So what we basically want is that we do not want parallel lines at all. We want to somehow construct a geometry where there are no parallel lines. Uh, so we, our set of points is basically the same as the points in R2. So we are working with the same set of points. So here I'm drawing the plane. So this is the plane R2. Say this is the x-axis, y-axis, and so on. Okay. And now, so in green, I'm going to draw two parallel lines, which are parallel in the Euclidean geometry, in the Euclidean sense. Now we want to somehow make these lines not parallel, and the one like very straightforward way to do this, a very artificial way to do this, is what we do is we define an artificial point in the for this direction. So both of these green lines say they have slope m. We know that like all lines, all parallel lines have the same slope. So let m be the common slope of these parallel lines. And we define this one red point to be the point at infinity. This is something we artificially constructed. This is not a point in R2. We define this to be a point at infinity. Uh, for we define one such point for each slope m. For each slope, we define one point at infinity, very far away, and we define that all lines of slope m pass through this point. Okay, so so according to our definition, when you extend these green lines, as they sort of extend, we are defining this one artificial point very far away, or like a point at infinity, and we say that like these two green lines meet at this point at infinity for slope m. And so now if I draw some different, so firstly, according to our definition, all lines parallel to the green lines, so sorry, this was a bad line. All lines parallel to the green line, so all lines with slope m would be passing through this artificial point we have constructed, and we are defining this to be the case. And suppose we consider a different set of parallel lines, so consider the blue lines, they are not parallel to the green lines, 1, 2, and so on. Then corresponding to the blue lines, there would be, so suppose the blue lines have slope slope equal to some m dash. Then corresponding to the blue lines, there would be a different point at infinity, and the blue lines would then go on to meet point at infinity. Okay, so corresponding to each slope, we have a point. We are defining a new point at infinity, which we'll call yeah. So just for the sake of some notation, I'll call the point x sub m to be the point at infinity with for slope n. So this would be point x sub m dash. Now notice that like for a line, there are two ways to extend a line, and you could have a priori just defined the point xm on the other hand. You can extend these two lines in the other hand as well. So, well, you could say that like why are you extending both the lines on and meeting them on one side? Why can't they meet on other side? And you're basically considering these 2 points to be the same. You don't want to like differentiate between like where you're extending. So there exists a point at infinity for each given slope, not each given like direction per se. Okay, so now our set of points. So set of points is R2 union these extra points at infinity. So x sub m for m slope. And these are the points at infinity. At infinity. So what are our lines? Lines. So you have lines in R2. Between any two lines, you have lines in R2. But what happens is, for a nice set of geometry, you would want to have that between any 2 points, there exists a unique line. Okay? And so far, like if you take 2 points in the plane, you know that there is a unique line, just the line, the Euclidean line. Between a point at infinity and a point in the plane. So consider x sub m and a point A here. You can just consider the line through A of slope n, and that would pass through x sub m. So this is the unique line through A and x sub m. But what happens? But what about lines between x sub m and x sub m dash? So you a priori so far we haven't defined any lines passing through two different points at infinity. And what we do is so lines in R2 union, we add this one extra line, which we'll call the circle at infinity, which basically, I'll draw it in purple. It passes through all the points at infinity, and it's a circular arc. The reason it's a circular arc is because you have the points at infinity are in, like, you can extend it in two directions. You're identifying them. So like you'll first start up with a you'll reach a semicircular region, but the two endpoints would be identified and you would get a circular arc. And this is what we call circle at infinity. This is one extra line that you're adding. So now your set of points is R2 union these extra points, which we call the points at infinity. Your lines are lines in R2 union the circle at infinity. And now you can see that between any 2 points, there is a unique line. And like if you there is a way to define distances and stuff quite nicely here. In fact, I can tell you what the notion of distance is here. So for R2 in the ellipse, so this is the, okay, so just for notation's sake, the set of points R2 union the points at infinity, and with these lines, this gives you this space is known as the real projective space in dimensions 2, known as the RP2. So real projective space. And this geometry is also sometimes known as the projective geometry. Now, how do you define distances between 2 points? So suppose this is a drawing of the RP2. Suppose you have a points A and B, A, B somewhere. You define the distance between points A and B to be the Euclidean measure of the angle between A, B, and the origin. And now so this notion of distance does seem quite tricky. Firstly, how do you define the distance between the origin and a different point, or like why is this a good notion of distance? Firstly, you would see that distance between points A and B is finite. Cannot be arbitrarily large. This can be at most 180 degrees, or like this is computed in radians. So we'll know like at most 2 pi radians. And secondly, like, so yeah, you can, like, for any point on a line through the origin, distance between, say, I let a dash be a point on the ray OA, the distance between a and a dash is 0, while a in a and a dash are different points, so a not equal to a dash. So yes, there are, like, this is definitely not a non-standard notion of distance, but, like, I'll get to why we define the distance in this way in a minute. But yes, so there is a notion of defining distance. There is a, you'll soon see a nice notion of defining angles and so on. But yes, this is a model of geometry. One can check that, like, this satisfies all the rest of Euclid's axioms. Note that I haven't stated all of Euclid's axioms here. I've just stated like a couple of them, but it is checked, and like you can check that like this model like satisfies all the Euclid's axioms apart from the parallel postulate. And about the parallel postulate, there are no two parallel lines because you have artificially made all parallel lines intersect at a point. So yeah, this is how we define elliptic geometry, and or it's also known as spherical geometry. And finally, the last, like, this may make the picture a lot more clearer. We will talk about why this model is known as spherical geometry, like where is a sphere coming in, where is an ellipse coming in, and so on. So the sphere, spherical geometry. So a priori, a geometry can have different models. Like, you can have, like, for Euclidean geometry, if you can have like some, you can consider a different set of points and a different set of lines. But if it satisfy, if your geometry satisfies all the axioms of Euclidean geometry, but just on a different set of points and lines, then you still call that axiom, like, still call that geometry Euclidean, and so on. So now we are going to define a different model for the projective geometry as we have defined, which is what is the standard model for spherical geometry. So what you do is you consider hemisphere. So I'm just drawing. So consider your sphere S2. So this is the unit sphere sitting in R3. Consider its bottom half. So bottom half of, like, this is a hemisphere. So let the center of the hemisphere be, I'll call this O, and at the bottommost point I'll draw a plane tangent to this point. Okay, okay. Now what you do is, from this, I'll call this point, say, O dash. Okay, now note that, like, for any point on from, like, if I draw a ray from O to any point on the hemisphere, I'll draw rays in green. If I draw a ray from O to any point on the hemisphere, I can extend this ray, and this ray will meet the plane in a unique point. So this gives you a bijection between points on the hemisphere and points on the plane. So suppose the points on the hemispheres are P and Q. This corresponds to P dash, some points P dash and Q dash. Similarly, if you have a line in the plane, not necessarily passing to the origin, but any line in the plane, then you can consider its pre-image on the hemisphere. and that would give you an arc, a circular arc, which is basically sort of a great circle. So this circular arc has, so basically there is a plane from O and this line L. You consider the plane joining O and line L. That plane will intersect the hemisphere, and that will give you a circular arc, which would be like an arc of a great circle. So uh, this is a great circle. Circle. And so on. So now, suppose the plane was given the projective geometry, as we have talked about earlier. And okay, now consider we can define this as follows, that a ray from the origin to like to a point on the equator. If you extend this, then technically it does not meet the plane, but we can define it to meet the plane at the corresponding point at infinity. So this would be at some xm. Like if I draw like a ray here, this would like in this direction meet at some xm dash and so on. Xm dash and so on. So basically, if you give the base plane the projective geometry of RP2, then you can sort of project project this geometry onto the hemisphere, and then the points on this equatorial circle would correspond to the circle at infinity, and points in the interior of the hemisphere would correspond to points on the projected plane, the real points on the projected plane. So now, with this in mind, let's look at the hemisphere. So now, on the hemisphere, your points are all the points on the hemisphere and all the points on the equatorial circle. The points on the equatorial circle, you are sort of identifying diametrically opposite points, because diametrically opposite points would correspond to the same point at infinity. So uh, on the equatorial circle, on equator, a point x would correspond to its diametrically opposite point minus x, would correspond to the same point at infinity, and the rest of the hemisphere is fine. You have like between any 2 points, you have a unique circular arc which corresponds to a great circle of the sphere. Uh, Now, distance between any 2 points is like, there is a formula. I don't want to go into the details, but it is basically a formula which depends on the angle measure of this circular arc, which seems natural. This makes sense of why it should be. The like if you have 3 points, say A, B, C, then the measure of angle BAC, the way you compute the measure of angle BAC in the spherical geometry is you consider tangents at A to arcs AC and BC. So these are tangent lines sitting inside R3 at A, and they would have some Euclidean angle. So spherical angle BAC, the measure of the spherical angle BAC is defined as the measure of the Euclidean angle. I'll call these tangents lines L1 and L2, make angle between L1 and L2. And you can have like Yes, so then you can define you have defined distances, you have defined angles, and so on. You can see that between there are no parallel lines because of points at infinity, and this gives you a geometry on the sphere. This is known as spherical geometry. This has some really interesting properties. Like, for example, on the sphere, you can have a triangle with all angles 90 degrees. I don't want to try to draw that right now, but yes, you can have this. And there's also stuff like distance between any 2 points, points A and B, is bounded. And this makes sense because like your distance is some function of the angle measure between on the great circle, and that is bounded by 180 degrees. So this makes sense. Um, Yes, there are a lot of other interesting properties I can talk about, but I think this is a good place to stop. We have defined um, what spherical geometry is. You can study more about this at many other resources. But yes, a priori, this also proves that the parallel postulate is indeed a postulate. Okay, thanks for watching the video and have a nice day.